guess it was over here for a reason. And then the last one, we have a moment arm again from my axis, which I said was on the left side, to where the force is applied of 8.814, positive 0.814, times 3.938, positive because it's up. And if someone would be kind enough to give me the parts and then the sum.
Okay, the first one I got 1.267972.
Good.
The second one I got negative 4.473469. Alright, the last one I got 3.205532.
All right, so we have torques from each of these forces, and if you add them together, three zeros or four zeros? 3.5?
3.5, yeah.
All right. What would the units be? Yeah, it's open to anyone.
Joules?
Not joules. Yes. When you're talking about energy and work, a Newton meter is a joule. But when you're talking about torque, a Newton meter is just a Newton meter. As you hopefully you can see, pretty darn close to zero. There is some rounding going on over there, so that would explain why it's not perfect. All right, so if we chose, any questions at this point?
If we put 0, would we still get it right? Or
Yeah.
do you, okay.
Yeah. Since, from an official point of view, I have 3 significant figures times 4 significant figures. So this should only be 3 significant figures, so the final answer should, when you add it, if you wanted to go by the strict chemistry rules of rounding, it would take out 2 decimal places. All right, now it should get the exact same value. You should also get 0 if I pick a different point. Because it adds up to 0, because it is in static equilibrium, static rotational equilibrium, some of the torques should be 0. So I'm gonna pick this point right here, 0.451 meters in from the left side as my new pivot point. The sum is the same. That part is still the same. I'm gonna just add up the 3 torques. What's gonna change are the moment arms. That's what's gonna change. So I'm gonna use magic of the eraser. Go to a different color just to emphasize it's a slightly different problem than what we just did. All right, so now the moment arm for the left scale. How would you find it?
And you said we're at 0.451?
Yes, that's where the new axis is.
Negative.
Yep. It's negative because if I go from my axis of rotation to where the force is applied, it's to the left, which I said is negative, and it's just the difference between that and that. All right. What is the moment arm for the weight? What is the distance from the axis of rotation to where the weight is applied? Yes. I'm hoping there are other people in here who realized it was 0 and just were too shy to say it, as opposed to you weren't quite sure what I was asking, but didn't want to ask anything. And then the last one, from the axis of rotation to the right scale.
Is it 0.549?
0.549, is that what you said?
Yeah,
How'd you get that?
I subtracted the 1 meter by 0.451. Nope, wrong, sorry. This is subtracted by the 8. Sorry.
363.
0.363?
Because it's in, not
Yeah.
on the edge.
Yeah. All right, now if we multiply these together, well, the first one I'll go ahead and do for you, 0. The one on the left will be negative. And the one on the right will be positive. I got that far. So it's going to be negative 1 point something.
I got positive on the other side,
Oh.
1.429494.
Okay, and on the other side?
Negative 1.42945.
429.
42945.
So we suddenly break apart at the 5th decimal point, or 5th decimal place. Hopefully that you can see this is pretty darn close to 0. And I assume someone's about to tell me what it actually is.
It's the same, 0.000035. One more 0, 4 zeros.
Units?
Newton meter?
Okay, so hopefully you've pulled out of this that the fact that ideally Where you pick your axis of rotation in this situation does not matter. Any questions before we do actual real life numbers? Where it won't look as perfect.
Did we do 0 because the axis is on that point?
Yes, absolutely. Jason?
When you're writing nanometers, or not nanometers, meters, do you have to do the dot on it?
It is preferred because since capital N is not a known prefix, you can get away with, if you write newtons first, not putting the dot in there. If you put meters first, you definitely need the dot in there because otherwise it looks like millinewtons. Oh. Oh, before I erase that. Getting back to the right-hand rules, let's see, okay, that acting down, that acting up. So in the first case right there, we established our sort system like that. So if I stuck an I hat, J hat, K hat would be coming out at us in a right-handed coordinate system. If this is my pivot point here, is this force trying to rotate it clockwise or counterclockwise? Yeah, and so counterclockwise would be outwards, so that first torque should be positive when we use D, as is shown. Oh, I erased it already. If this is my pivot point here, which way is this trying to rotate it? Clockwise or counterclockwise? Yeah, clockwise. So if I rotated my fingers clockwise, about that point, my thumb would be pointing into the board, so you should get a negative torque, which is what we have right here. This right here, if that's my pivot point, this isn't trying to rotate it at all, it's like pushing on a hinge. Not particularly successful in opening or closing a door. And this one right here, clockwise or counterclockwise? Gabby?
Counterclockwise?
Yeah. Which has the thumb pointing outwards, which makes it a positive torque. So the other way that you could do this, you could also, instead of setting up that convention, you could just say, well, if we make counterclockwise torque positive and clockwise torque negative, you could just do the distance times the force and then think through it and go, okay, that's a clockwise torque, I'll put a negative there. It's a counterclockwise torque, I know that's positive. All right, so here we go, real numbers from an actual lab. We have a meter stick. The mass of the meter stick is 143.2 grams. The force at the left scale, and this is 10.0 centimeters. Force from the left scale is 0.685 newtons, and the force from the right scale, 0.695 newtons. The position of the center of mass, 90.0 centimeters, and the position of the center of mass of the meter stick is 49.9 centimeters. First, let's look at the sum of the forces. It is in static equilibrium as inspected, as in we're looking at it, it's just hanging right there. All right, I know the two forces that are acting up, that's just given to you. And in a lab situation, you would just read that off the lab quest. So here's my left scale, this is 0.685 newtons, and my right scale, 0.695 newtons. There's gotta be a force acting down. What is that force?
Weight.
Okay, and what is the value of the weight? Well, same formula as before, W equals mg, which is 0.1432 kilograms times 9.798 meters per second squared.
One point 40307736.
40307336 units. Yes. All right, so I know ideally the forces up equal to forces down. However, in a lab situation, it doesn't always work out as nicely. So let's take a look at the forces acting up. We have 0.685, 0.695. Add those together. 0, carry the 1, 8, carry the 1, 1.38. So we have 1.38 newtons acting up, 1.403 newtons acting down. A little bit off. How far off is it though? Yeah, we could go through and find the difference of them, but if I'm lining up a bunch of forces and I say that, you know, we're off by 0.02 newtons, is that a big number or a small number? It depends. If I'm looking at the forces holding molecules together, that's a huge difference. If I'm looking at the forces acting on the Golden Gate Bridge, that's not much. So we have to compare it to something. So what I'm going to do is, what I'm comparing is 1.380 newtons. And the other force is downwards, negative 1.403 newtons. I want to compare the absolute values. So I'm going to compare the 1.380 and the 1.403. And so first thing I do is I take the difference. I'm not caring about which one you subtract from which, so I'm just going to take the larger minus the smaller. But then I need to compare it to something that has some significance here. And I really don't know what it's supposed to be. I don't know whether the mass of the meter stick is off, or the force scales are off, or whether physics is complete bunk, which I'm assuming is not the case. So I'm going to divide by the average of the two numbers. This is a percent difference. And you end up with, and then put it in percent form, times 100%.
This has nothing to do with this, but did you grade the homework quiz yet?
Yes, I did.
Okay. Can we get them after class?
Yes, we can do that.
12.8%.
12.8. Oh, that seems awfully high. Anyone else get 12.8?
Is it because you switch the, on the top, on the numerator, you switch the values around?
That would just give you a negative sign if.
Yeah.
What did you get, Yvette?
I got 0.41%.
Percent? difference about 0.02. Yeah, 12.8 just does not seem right. Anyone else get 12.8 or 0.4? You got something different, Ashley? You got 12.8.
I got 0.1.
Well, I
Okay, so
multiplied that.
the top
by
two
the 12,
numbers,
the
I
0.4.
got, the top two numbers where you minus them,
Right.
I got 0.023.
And the average will be 1.39 something.
I'm sorry, I'm redoing it from. So when I add them together, it's 2.738, then I'm gonna
Divide by 2.
divide by 2. And then I get, 2.093.
No.
Oh, I
If you
did it
divide
wrong,
by-
sorry. Divide by 2, 1.39,
39.
15.
And then if you do that,
Let's see if I messed up.
you got 0.128.
Yeah, and then I multiply it by 100 to get 12%. 12.8%. Or I didn't do that part.
So 0.023 divided by 1.3915.
Yeah.
I got 0.0165 if I round up.
That's
And
what I
then
got
if we
too.
times it by 100,
You
we get 1.65. Right?
Yeah, that's what I got.
That's
You
what she
got
got.
Clint?
She had the right.
Yeah, I'm not quite sure where the 12 came from. 1.41.
I got,
I divided by 0.5 instead of 2. I know what I.
Ah, okay.
I did, I got 0.12